Okay, so for section 3-4, parallel and perpendicular lines, okay? So this is building off of the lines and angles that we've already been talking about with parallel lines cut by transversal. And so now we're going to introduce something new. So we've been talking about parallel. Now we're going to talk about perpendicular lines. And you may have heard of perpendicular before, but we want to make sure we get the clear definition of what perpendicular lines are, because this is very important, just like I've been always saying. The rest of geometry builds on these concepts. So understanding points, lines, and angles and those types of things are very important for the rest of geometry. So put in the work now, okay? So for perpendicular lines, we can see our picture here. It's two lines that intersect and form a right angle. We know right angle means 90 degrees, okay? I will be asking this question a lot. What are perpendicular lines? Okay, and the key things here is that they intersect and form a right angle. Okay, intersect, form a right angle. The symbol for perpendicular is this upside down capital T. Upside down capital T. So we can say line A is perpendicular to line B. And so if those two lines are perpendicular, then there's a 90-degree angle. Okay, so automatically every time we see the little perpendicular symbol, we should think that there's a 90-degree angle. Okay, so for example, we've already talked about how we cannot assume 90-degree angles. So we can't assume that, let's say, R and S are form a right angle here. But if this problem says R is perpendicular to S, well then, I know that this angle is going to equal what? Well, it must be 90 degrees. And then let's use that logic all the way around. This is a straight line, so what do I know this straight angle is going to equal? Well, it must equal 180. So if part of it's 90, then what's the other part going to be? Well, that must be 90 as well. And we could do that all the way around here. Well, this is vertical. Okay, so I found this one because straight line, supplementary angles equal 180. Well, this one is vertical to this one. So this one must also be 90 degrees because vertical angles are congruent. And the same logic here. This one must also be 90 degrees. And we could either use the vertical angles or the supplementary angles right here, no matter what. So in every single angle, if the lines are perpendicular, then they form a 90-degree angle. That's how that works. It's also really important why we can't assume 90-degree angles, because if one angle is 90 in here, then they're all 90. So the little square represents two lines being perpendicular and forming a 90-degree angle. So if a problem asks you, what do we know about this picture? You can't just be like, oh, I know that angle is 90. That also means that they're perpendicular. So if it gives you this, line L and line M, and it asks you, what do you know about them? Well, I know line L is perpendicular to line M right there. Okay, that's a very important thing to understand, is that the box tells us they're perpendicular as well as being 90 degrees. Because if it's 90, it's perpendicular. And if it's perpendicular, then it's 90. It works both ways, okay? So then we have three theorems that go along with parallel and perpendicular lines. So our first one being, and these are if and then statements because they're theorems, and that's how we usually put these. So I say if A is parallel to B, and we can see that on this picture, the extra set of arrows, right? That's what shows they're parallel. If A is parallel to B and B is parallel to C, then A must be parallel to C. You can see that right here. In this case, we can even see they look parallel, right? This theorem just says they are parallel. If they're both parallel to B, then they must be parallel to each other, okay? This next one, if E is perpendicular to F, so we can see that because of the box. So up here, the arrows told us they were parallel. Right here, the box tells us that they are perpendicular. So if E is perpendicular to F and E is perpendicular to G, meaning that both of these are perpendicular, then we have F is parallel to G. Now, the way I'm going to prove this to you is, can anyone think about what type of angle pair these are right here? Okay? If in theory these were parallel lines, okay? cut by a transversal, what type of angle pair would they be right here? Let's work through our logic. Well, one's on the interior, one's on the exterior. They're on the same side of the cutting line. Well, it looks like they're in the same spot in a different group. So they must be corresponding angles. And if we think back to 3-3, we know that if we have corresponding angles that are congruent, and we know that both of those angles are 90, then the lines must be parallel. This is just following that exact same rule, but we're just using perpendicular here for those congruent angles. Okay, the last one actually has a name. So these two, we're not too worried about what they're named, and so we don't need to stress too much about that. This last one does have a name, and we use the name. It's the perpendicular transversal theorem. And so the way we write that is an upside down T and then capital T, capital T. Okay, it's a lot of T's. So this is perpendicular transversal theorem. And we use this to say if the lines are parallel and L is perpendicular to T, okay, so L is we can see that right here. These two lines are parallel because the arrows, and the line L is perpendicular to line T right here. Then M must also be perpendicular to T. So there must be a little box right here as well. That's what this is saying must be true. The reason why this is true, it works out that same thing. If the lines are parallel, then we know corresponding angles are congruent. So if this angle is 90, the corresponding angle must be 90, making those two lines perpendicular. So that's how the perpendicular transversal theorem works. We call that one by its actual name when we use it, which is important to know. And if you don't want to write out perpendicular transversal theorem, this is our abbreviation for it. And I still will know what you're talking about. That might be a little difficult to write on the computer if you're writing it. So maybe just say perp for perpendicular if you want to abbreviate it further. Perpendicular transversal theorem. Or just spell it out as we have here. Now, for the textbook problems, especially with 16 through 23, it's important that you draw it out. And I'm going to talk about that real quick right here. So on 16, it says that A, B, C, and D are distinct lines on the same plane. We're trying to figure out how A and D relate. So I want you to draw it out. Now, this could just be a rough sketch. You don't have to draw it out with all the arrows and line names and everything. But it says if A is parallel to B, so I can draw A and B. I want them to be parallel, so they're next to each other. And then it says B is parallel to C, so let's make another line right there. C, that's parallel. And C is parallel to D. Then we're focused on how A and D relate. Okay, that's all we're doing. And I can see very clearly that they are parallel. And that's using our first theorem, right? That doesn't actually have a name, but it does, but we're not too focused on the name. We can see that they're parallel. This is your justification. So you see how it says justify your answer? You drawing these pictures, that's your justification. And I can say A is parallel to, nope, not B. Let's fix that. A is parallel to D, because that's what it's asking about, how A and D relate. In all of these, they're either going to be A is perpendicular to D or A is parallel to D. I will tell you that right away. And your picture is going to justify it. That's your reasoning, okay? So that was what 3-4, parallel and perpendicular lines, is all about.